Bismillahirrahmanirrahim. Assalamu alaikum students. We know the first law of thermodynamics. We have discussed it. It says the first law of thermodynamics. We have done this in previous lectures. The first law of thermodynamics says what? dq is equal to du plus dw. What is dq? Net heat put into the system. What is du? It is net heat put into the system. This du is change in internal energy. dw is work done by the system, right? Net heat put into the system. du is change in internal energy, and dw is work done by the system. So we said that, or I can write it this way. First, let me first do this. We said it is the statement of conservation of energy. It is the statement of conservation of energy, right? We said if we put some heat into the system, if it does no work on the surroundings, then that heat will be used by the system in increasing its internal energy. Or if there is no change in the internal energy of the system, that heat put into the system will be used by the system in doing work against the surroundings. Our third possibility is the heat put into the system will be used by the system partly in enhancing its internal energy and partly in doing work against the surroundings, right? So remember this. Now if I write it, I can write this equation this way also. Let me use this color, green. I can write it dq minus dw is equal to du. You know our sign convention. Here our dw is positive. So we interpret it as work done by the system. And negative work we interpret as work done on the system by the surroundings, right? So this way you can interpret it this way also. So interpretation will be, I said dq minus dw is equal to du. dq minus dw is equal to du, right? What is the interpretation now? It is net heat put into the system, net heat put into the system, right? Now, according to a sign convention, now this minus dW is what? It is work done on the system, not by the system, on the system by the surroundings. And what is du? It is change in internal energy of the system, right? So dq is net heat put into the system, minus dw is work done on the system, and du is change in internal energy of the system. That means if I want to change the internal energy of some system, either I can put heat into the system, that will change the internal energy and I do no work. That's one way. Second way is I don't put any heat into the system, but I do work on the system in order to change its internal energy. Third possibility is I partially put heat into the system and partially do some work on the system in order to increase its internal energy, right? Now there is one thing, heat and work. I write here heat and work are equivalent in one sense. Which sense? That sense is this sense. If we want to increase the internal energy of a system by 10 joule, I do no work on the system, so that is, this is 0. I can put 10 joule of heat into the system, its internal energy will increase by 10 joule, right? Second option I have, I put no heat into the system, 0. I do 10 joule work on the system and its internal energy will increase by 10 joule. So in this sense, heat and work are equivalent. That means if I want to increase the internal energy of a system by some amount, here I have taken a 10 joule, I can either put 10 joule heat into it, or I can put 10 joule work on it. I can do 10 joule work on it. That means for a given increase in internal energy, I have to either put some same amount of heat into the system or same amount of work I have to do on the system. So in increasing internal energy of the system, heat or work, these two options are equivalent, right? Now question is, are heat and work equivalent in reverse sense? What is that reverse sense? Now question is, are heat and work equivalent in reverse sense? What is that reverse sense? Let me go back. I write it dq minus dw is equal to du, right? dq minus dw is equal to du. So one sense was I increased the internal energy of the system by either doing work on it or putting heat into it. So that way heat and work are equivalent. Now reverse. Reverse means if I want to decrease internal energy, decrease internal energy, right? Get work out of that. Get work, get work out of that. Or get heat out of that. Get heat out of that. That means, let me use the numbers. If I decrease the internal energy of the system by 10 joule, right? And I get no heat, can I get 10 joule of work? Second thing is, if I decrease the internal energy of a system by 10 joule, I get no work, can I get 10 joule of heat from the system? Now what do you think? Are heat and work equivalent this way also? Try to understand my point. First I said heat and work are equivalent in one sense. Which sense? I can do 10 joule work on the system, no heat put in the system, internal energy of the system will increase by 10 joule. Or second option, I can put 10 joule heat into the system, I do no work on the system, and I get the increase in internal energy of the system by 10 joule. Now I am doing reverse. I am decreasing the internal energy of the system. I am saying if I decrease the internal energy of the system by certain amount, is it possible to get no heat and I get complete work? And reverse also. That means I get no heat, I get work, or I get no work, I get heat only, right? Or heat and work equivalent this way also, or these both possibilities possible. Now it turns out, the important thing is, it turns out that there is no difficulty in taking internal energy of a system out of a system in the form of heat. That means this is possible. That it is possible that you decrease the internal energy of a system and get that much amount of heat from the system and get no work, right? But this thing, which thing? That it is that you decrease internal energy of a system and get work out of that, right? Without getting any heat. Got it? So I'm saying it is impossible to convert this internal energy completely into work, this option, without any change taking place in the surroundings. So this option is impossible. You cannot decrease internal energy of the system and completely convert that to work. When you do this, some other thing happens in the surroundings, right? Some other thing happens in the surroundings always. You cannot get this 10 joule and this 0. This is impossible. So heat and work are not equivalent in this sense. Not equivalent. Heat and work are not equivalent in this sense. This was first point. Second point is there are certain processes. There are certain processes which never occur in nature. For example, if you have this cup, hot cup of tea or water, you place it in your room, your surrounding air in the room is surrounding, air in the room is surrounding of this cup, this hot cup of tea is your system. What you observe when you place hot cup of tea or water in your room, it automatically, spontaneously cools down. It spontaneously cools down. What happens? It has larger temperature than the surrounding air, so it loses heat. Heat moves from this hot cup of tea into the surrounding air, and this process is spontaneous. It occurs by itself. There is no external intervention required for this process, right? So it's okay to happen because first law of thermodynamics allows it. Why first law allows it? Because first law of thermodynamics is basically statement of conservation of energy. So it loses energy, that energy goes in to the surrounding air, right? It's okay. Total energy is conserved. The amount of energy which disappears from the cup appears in the room. There is no issue with the first law of thermodynamics. But if reverse happens, still there is no issue with the first law of thermodynamics. That means you have this cup of tea, hot cup of tea or water, and you have this surrounding air, room is surrounding. This is system. Surrounding is cool. System is hot. We said What happens spontaneously? It loses heat that goes into the surrounding air. Total energy is conserved. The amount of energy lost by the system appears in the surroundings. So no issue with first law, because that first law is the statement of conservation of energy. Now I am saying that reverse process is also possible according to first law, but never occurs. That means if heat moves from cold surroundings to the hot cup of tea, there is no issue with the first law, because if heat disappears from the surroundings, that will appear in the cup of tea. Total energy still remains conserved, so there is no issue, right? But reverse process never occurs by itself. Remember it. That means you never see that you place a hot cup of tea in the room, it becomes hotter with time by itself, and surrounding air becomes cooler with time. You never see it by itself takes heat from the surroundings and heats itself, even when such process is allowed by the first law. So these two things you need to remember. First thing I said, that in one sense, heat and work are equivalent. I can put heat into the system and increases in internal energy. I can put, I can do work on the system, increase the internal energy by same amount. In other way, in other sense, they are not equivalent. It is impossible to decrease the internal energy and get equal amount of work from that system without getting any heat. But this is possible, that internal energy of the system decreases by some amount and we get heat, same amount of heat from the system with zero work. So heat and work are not equivalent in this sense. First point was this. Second point is that there are certain processes which should occur or which are allowed by the first law but never occur in nature. So I have given the example that if I place hot cup of tea or water in cold surroundings, this never occurs, that this cup becomes hotter with time and surrounding becomes cooler with time by itself. So such processes doesn't occur. That means there is more to first law of thermodynamics. So reason for these processes and these whatever we pointed out in thermodynamics to explain this or to justify these things, we have another law that's called second law of thermodynamics, right? Second law of thermodynamics. Now, second law of thermodynamics, we will see have many statements, but all those statements are equivalent. We will give here statement in terms of heat engines. So I write here heat engines. and second law of thermodynamics. Because my statement will be in terms of heat engines. Now you also know this, that what is heat engine, and first heat engine which was invented was steam engine, right? So what steam engine or any other engine, there are other types of engines, diesel engines, internal combustion engines. But what these engines do basically, they take heat, do work, and reject some heat. I repeat, all heat engines, what they do, they actually convert heat to work. They convert heat to work. We put heat into them, they do some work for us, but in the process, they reject some heat. So, schematically, thermodynamically, all these heat engines are equivalent, and schematically, we represent them this way. I draw this figure. Then I will explain. Razor, pen. Let me fix this. What happened? Okay. So I will use actually different color for this. How we schematically represent a heat engine, right? Let me use this color. Engine or heat engine. This is my hot reservoir, hot reservoir at temperature T subscript H. This is my cold reservoir at temperature Tc. So first I write the, let this be QH, let this be W. Here it is QC but in modulus. This is a schematic representation of heat engine. I explained to you, for example, if you take the example of steam engine or any other engine, in these engines there is some working substance, some working substance. That working substance in case of steam engine is water. What we do, we put some heat into the working substance. Now that heat will be put into the working substance or into the engine by some other system. Now that system we call hot reservoir, and that hot reservoir will have some temperature. which we have denoted as TH, right? TH here is temperature of hot reservoir. Sometimes in some books, you will see we call it source, heat source, right? So my working substance takes some heat from the hot reservoir whose temperature is TH, or the source of heat whose temperature is TH, right? Then it undergoes some process. During that process, it does some work for me. W is the work done by the engine. When it does work in the process, during that process, it also rejects some heat. That heat rejected is my mod of QC. And that heat is rejected by the engine to other system. That system is represented by cold reservoir. That has temperature Tc. So Tc is temperature of the cold reservoir, and this cold reservoir is sometimes called sink. This is called source, hot reservoir. Cold reservoir is called sink. So I have an engine, any engine. That engine has some working substance. It basically does what? It takes some heat, that is QH, does some work, that is W, and in the process it rejects some heat, right? That is the mechanism. And in this process, the working substance comes back to its initial state. So we say these engines are cyclic because working substance comes back to its original state. So the process is cyclic. Engine is cyclic. So in each cycle, it takes certain heat, rejects some heat, and does some work. Right? Now, if I apply first law of thermodynamics to it, first why I have put this in the modulus, because I am interested, when we represent heat rejected by the system, according to our sign convention, we take its sign as negative. Negative Q means heat rejected, right? So QC, I have put, if I take its sign, then it is negative, but I am taking only modulus, because I am interested in the amount of heat. So what is QH minus QC? QH minus QC, QH minus QC mod, means amount of that heat, is simply net heat put into the system between the engine. That is my system in each cycle. In each cycle, working substance or engine takes this much heat, rejects this much heat. So I've subtracted. This is my net heat put into the system, which is engine, in each cycle. And what is W? W is work done by the engine, which is my system, in each cycle, right? Applying first law of thermodynamics, applying first law of thermodynamics. First law of thermodynamics says net heat put into the system is equal to work done by the system plus change in internal energy of the system. Now, since internal energy is a state function and the working substance of my engine undergoes cyclic process, in each cycle it starts with certain state and then comes back to that state, and during that cycle net heat put into the system is this much, work done by the system is this much. Since it is process is cyclic, internal energy is state function. Therefore, what is the change in internal energy? Change in internal energy is zero. That means net heat put into the system must be equal to work done by the system. That, in other words, means if I write first law for my working substance for my cyclic engine, I will write QH minus QC net heat put in the system is equal to W. Right. Now we define efficiency of the heat engine. The efficiency of the heat engine is defined as, we represent it by the symbol epsilon, and it is defined as the ratio of W to QH, right? Ratio of work done by the engine in each cycle over heat put into the system, not net heat put in the system. Heat put into the system or absorbed by the engine from the hot reservoir. I can replace W by what? I can replace W by QH minus mod QC. It will be first, then I have downstairs QH, so I'm using first. I use it first here. I can write it efficiency is equal to, I divide by QH 1 minus QC by QH. This is the expression for efficiency. So efficiency of a heat engine is 1 minus QC by QH. Now what we want? We want our heat engine to be efficient. If it is 100% efficient, that will be best possible situation. 100% efficient means, let us go to the diagram, that if I put certain heat into the engine, I must get that much work. There should be no heat rejected by the system, because this heat rejected is a loss for me. I want work, not heat. So 100% efficient engine means if I give 100 joule heat to it, it will give me 100 joule work. No heat will be lost to the surroundings. That in terms of the equation means this is 0 and efficiency is 1. QC should be 0, efficiency should be 1. Or QH and W must be equal. That is possible when QC is 0. That engine is 100% efficient. But that is not possible. Over time, since the invention of the heat engine, we have been able to improve the efficiency of our heat engines, but we have understood this thing that it is impossible. There is a restriction in the nature. It is impossible to make 100% efficient heat engine. So that is the one statement of second law of thermodynamics. And that statement has a name. That statement is called Kelvin-Planck statement of second law of thermodynamics. So I write Kelvin, Planck. These are two people, Max Planck and Lord Kelvin. So Kelvin-Planck statement of second law of thermodynamics. Kelvin-Planck statement of second law of thermodynamics. So I write the statement, then I explain, or it is already explained. It is impossible for an engine, that is heat engine, working in a cycle to produce no other effect than that of extracting heat from a reservoir and performing an equivalent amount of work. Understand this statement. We said we cannot have a perfect heat engine. That means efficiency of a heat engine cannot be 1. That in other words means it will always reject some heat. You cannot make QC 0, right? This we have Max Planck and Kelvin have put into this statement. It is impossible for an engine working in a cycle. Working in a cycle is important because our engine is working in a cycle. That's why we put 0 for change in internal energy to produce no other effect. That other effect it will always produce, that is rejection of heat, than that of extracting heat from a reservoir and performing an equivalent amount of work. So it is not possible for an heat engine working in a cycle to take heat and convert that heat completely into work. It will always reject some heat. This is one statement of second law of thermodynamics which you need to understand. Now I will give you a homework. Your homework is like this. Question. A quantity of air, a quantity of air expands adiabatically and quasi-statically from an initial pressure from an initial pressure of 2 atmosphere and volume 2 liter and volume 2 liter at room temperature at room temperature 20 degrees Celsius to twice its original volume. To twice its original volume. What are, change the color. What are the final pressure and temperature? It is given for air, gamma is 1.4. So I repeat the question. A quantity of air expands adiabatically and quasi-statically from an initial pressure of 2 atmosphere and volume 2 liter at room temperature 20 degrees Celsius to twice its original volume. What are the final pressure and temperature for air? Gamma is 1.4. We have done the expression, or we have derived the expression for work done by an ideal gas. It is if it expands adiabatically. We have to use that expression to solve this question, and you know this gamma is what? Cp by Cv. The ratio of heat capacities. Cp stands for heat capacity at constant pressure. Cv stands for heat capacity at constant volume. This is all for today. Thank you. God bless you. Assalamu alaikum.